I have a lot of slides, and we used a lot of time on this mic, so we're going to race through this presentation about HTTP. I'm Daniel. I'm one of the co-founders of Objective-CIO, and currently I have to make some ad for the core data book that I'm writing with Florian. I usually do talks about core data, and this time it's about something else, but you should all buy the book so that Florian and I can get rich. So that you can learn about core data. And it's going to be awesome, and it's going to be out soon. But enough about core data. We're here to talk about something else. It's not just HTTP. Actually, we're only going to touch very briefly upon HTTP, but we're mostly going to talk about IP and TCP, and a little bit about some HTTP2 and TLS. So what is all this about? Well, it's about this kind of thing. It's about the internet. How does the internet work? The internet is this amazing thing. So often we use it like this. You have a browser, you browse your favorite web page. But since we're developers, if you think about it, whenever your app sends data to a server or wants to get data from a server, you're probably using something like this or some other framework around it that does HTTP requests. Very few apps use anything else but HTTP to send data through the internet. So there are other things in the internet than HTTP, but for us, that is really the workhorse of the internet is really HTTP. So in the internet, in the standards, there's a talk about a stack, and a stack. There's something called open systems interconnection. They define the standard with kind of 7 layers, and some of the layers look like this. So you have an application layer that sits on top of a transport layer, that sits on top of the internet layer, that sits on top of the link layer. And the particular stack that is kind of more familiar to us looks something like this. So on the application layer, we have HTTP. HTTP runs on top of TCP, which is our transport layer. That runs on top of IP. It runs on top of Ethernet, usually. And so what does that look like in practice? Let's say we have the string NSSpain, and we want to send that through the internet, which is HTTP. So that would look something like this. You take your payload, our string NSSpain, we put that into HTTP. Then we put that into TCP, which puts another header on front. We put that into IP. And then this entire thing is what actually gets sent through the internet. So you have this kind of layer of things that get put on top of each other. And what we're going to look at is kind of take it from the inside out. So the first thing we're going to look at is IP. And IP is really just short for Internet Protocol. And it's really what the internet is. And this was invented a long time ago, in 1974. And back then, computers looked something like this. This is actually just the drives of a computer. The computer is standing somewhere in the back. And this was kind of the state of the art when IP was invented, but we're still using it today. And what IP is, it's packet switched networking, which is kind of cool thing. IP is very, very, very simple. It defines hosts, which is just a different name for computers. And nowadays an iPhone is a computer too. And then it defines something it calls datagrams, which is just packets of data, relatively small packets of data. It's about 1 kilobyte. And then it kind of defines how do you send this packet from one computer to another. And in doing so, each computer needs to have an address. And this is where the term IP address comes from, because that's the address in the IP world that a computer has. And in IPv4, it looks something like that. In IPv6, they're look differently, a bit longer. But that's just kind of the identifier of a computer. So if my computer wants to send a packet to Apple's computer, then my computer has IP address 1 and the other one has 2. And so I can send a packet from IP address 1 to address 2. That's really what IP addresses are all about. So you kind of know where things are coming from and where they're going to. And then IP defines a kind of best effort approach. So we have these small chunks of data that we can send. So my computer can send this packet, and it may be lost. It may arrive multiple times at the other end, and if I send multiple, they can arrive in some random order. IP doesn't care about that at all. It's kind of most of the time these packets will arrive, but it's just kind of fire forget. My computer will take this small chunk of data, put it on the internet, and forget about it. There's no state about I have sent these. The other guy doesn't tell me if it has received or not. IP doesn't solve any of that. It's just small chunks of data that maybe reach the other end. And that sounds kind of very limited. But that's really all of the internet is based on top of that. So next thing we're going to talk about is TCP, which is Transmission Control Protocol. It's kind of a lot of big words. And you've probably all heard the term TCP/IP, and that is because almost everything in the internet, including HTTP, is using this combination of TCP and IP. And that is really what kind of revolutionized the way you could use the internet. And this was invented back in '81, and kind of the heroes of the day back then kind of looked like this. This is Bill Gates and Paul Allen in '81 when they didn't invent it, but they were around back then. And you can see computers didn't look all that different from '74. I don't know. I have no idea what they were doing. But those were kind of the cool heroes of the day. So it's also a very old protocol, but that's really what's been enabling all the crazy stuff we can do nowadays in our apps. So what TCP gives us is kind of very different from IP. It gives us a delivery of stream of data between programs. So I can send an unlimited amount of data from a program to another program. It's reliable and it's ordered. TCP guarantees that the data that you send will eventually receive the other end. And it will get there in the exact same order that it was sent. This may seem very trivial because we do that every day, but it's a very stark contrast to how IP works. TCP sends data from one program running on one computer to a program running on another computer. IP just sends data from a computer to another computer. It has no concept of which program is talking to which program. And IP is unreliable, where on the other hand, TCP is reliable. It guarantees that the data gets there. And again, IP is unordered, TCP is ordered. And the remarkable thing is that TCP achieves all of this even though it runs on top of IP, which is not very reliable or any of that. And how does it do that? Well, if we look at how can we send unlimited amounts of data, it's sort of obvious. IP packets have a limited size. So what TCP does, it takes a large amount of data, it cuts it up into smaller chunks, and then adds a header on top, which turns it into, and that makes it a TCP segment. And those segments are of a size that fit into an IP packet. So what does that look like? If we have a JPEG file, you might have to cut it up into 4 pieces. We take those 4 pieces, we add the TCP header in front of it. So if you look in a bit more detail, we have the payload, which is part of our JPEG data, and then the TCP packet, what it has in it is the sort and destination port. We'll get back to that in a bit, but that's kind of how you can send data between programs and not just computers. And then it has a sequence number. So each packet, each segment has a sequence number, so it'll be segment 1, segment 2, segment 1, segment 2, and segment 3, and the sequence numbers. That is how TCP does the ordering stuff. And then in front of that, we put our good old IP header, which is what we had before, where we have the source address and the destination address. So that is how TCP can send unlimited amounts of data. It cuts it up. Now, the next thing is that TCP has state. It has a connection where one program is connected through a stream to another program. So TCP has a connection where these two programs are connected to each other. So now they can actually send data through this pipe that TCP really provides. And it's TCP is always duplex, so once these two programs are connected through the internet, they can both send data through the same pipe, and the other ends will receive it. And because it's programs, even though it may seem trivial, but what TCP gave us is that we can have multiple programs on the same host talking to each other independently. If my iPhone talks to Google server and requests a JSON, and at the same time asks the same server for a JPEG, the connection that asks for the JPEG is going to get the JPEG back. The one that asks for the JSON is going to get the JSON back. So it's this separation, and that is what TCP provides. So it's really the connection is defined by the combination of the address, so both machines have an address, but then the programs have the port number. So you all probably know that if you connect over HTTP, you connect to port 80 on that machine, but the connection that you create on the side that creates the connection picks a random number as its own ephemeral port number, and that is the connection that's identified by my address and port and the other side address and port. So if I have another connection, it can connect to the same server, also port 80, it'll just have a different number on the sender side. Connections are super complicated. We're not going to talk about it, but they have all kinds of states and can transition between them. That part is sort of boring. One thing that's important to know as an app developer is that TCP connections need to be created. They don't just exist. And creating a connection requires a three-way handshake between the server and the client that talks to that server. And I'm going to gloss over a lot of the details. But as you remember, each TCP packet, each segment has a number. So what happens during the connection setup is that the machine that connects and the other end agree which numbers they want to start with. So for some reason, TCP doesn't always start with, like the first segment is not called number 1, but we pick a random number. So what happens is that the guy on the left wants to connect to the guy on the right. It sends a so-called syn packet, which means synchronized sequence numbers, and it tells the other guy, I want to use 2,777 as the first number. The other guy then sends back, hey, I got that. It, for some reason, adds 1. That's just how they implemented the protocol. And it says, I want to start synchronized. I want to start with 587. And then the first guy says, I got that. Here's your +1, 588. And because each packet has a sequence number, this one will have the first one +1, because that is the next packet that got sent. And with this, the two machines are connected. They have a TCP connection. And now both sides can send data. And each packet, each TCP segment will then keep incrementing these sequence numbers. So that's kind of a very short definition of how the connection startup works. After that, these sequences are actually sent, and the sequence numbers here was a bit lazy, so I started with 10 instead of some weird number. And the sequence number increased by the number of bytes that were in that packet. And here it's only host A sending data to host B. And part of what TCP does is that the other side will acknowledge, it sends an ACK package for all the data that it receives. In reality, this is super complicated, but TCP uses that to achieve the reliability. So this way, the first host can figure out if all the data made it there, and the sequence numbers allow the receiving side to reorder sequences whenever they're received out of order. So That's kind of the very simplified view of that, of how that works. And also, because there is a delay in the internet, the one host will just keep sending segments, and eventually the other end will acknowledge them. There is a delay. So like here, I'm kind of showing that the first host sends 3 packets, and only then does it receive the response from the other end. And that, of course, depends on the delay that you have on the network. So in reality, TCP has to do a lot of magic to get all this working. And as you all know, the speed of your internet connection is limited. The bandwidth that you have is limited. And what TCP, the clever algorithms in TCP make sure that you use as much of that bandwidth as there is available, because if you've paid for a very fast internet connection, you want to use that. But at the same time, TCP makes sure that if you have multiple connections, that they can all live on your internet uplink at the same time. So there is this fairness, which is in the algorithms. TCP does a lot of clever things to minimize latency. So as packages get sent to the other end kind of sees how quickly does it receive acknowledgements. And based on that, it makes some fair guesses that if one of these acknowledgements that come back is coming at a kind of, is missing, it doesn't request that one packet again immediately, and it kind of waits a bit, and how long it waits and all that is based on kind of what does it look like. So if all these acknowledgements take, let's say, 1 second, then it may wait 1.1 seconds until it re-requests them. Or if there's a lot of jitter where some of them arrive very quickly and some later, it looks at all these things and makes some guesses on how quickly should I kind of consider the package as lost. So there's about a 6,000 word RFC document that describes how a lot of this stuff works. And I don't even understand it. Yeah, that's the slide for that. It's super complicated, but the main concept is just kind of, it looks at kind of what happens on the wire continuously, because the state of the connection changes. Just imagine you're downloading the Xcode 7 disk image from Apple. Then TCP will just try to download as much as possible, but then at the same time you're like, well, there's also an update for El Capitan, so I'm also going to download that. Then TCP will automatically reduce the number of packages that get sent through for your Xcode disk image and give some more space to the other one. So it continuously adapts that. Or you switch from Wi-Fi, from a good Wi-Fi connection, you walk somewhere with your laptop where the connection is poorer, it kind of has to adjust for that. And all that magic happens in TCP, in its congestion control and flow control. Yes. TCP runs on top of both IPv4 and IPv6. It's the very same TCP. TCP doesn't really care which one it is. And how are we doing on time? 20. With that, we're browsing onto HTTP. So HTTP, as you probably know, was done in CERN. Actually, it was, I think, the first browser that used HTTP was running on a Next machine, which is sort of the same software that's now on the iPhones, more or less. That was back in '89 or something, and HTTP doesn't have to, but for all intents and purposes runs on top of TCP, and TCP again runs on top of IP. We're not going to talk a whole lot about HTTP, but it's basically a very simple request-response thing, as hopefully you know. It's the client sends one single request, and the server sends back one single response. That is the entire concept of HTTP. You can then send another request and get another response, but there's always this request-response pattern in it. It's mostly ASCII-based, which was, like, it's sort of readable, and that was just how people would design these kind of protocols back in the 80s. it sort of depends, and nowadays it's not entirely true anymore. But if you've probably seen an HTTP request, here we're getting the Objective-CIO about page. And this is the request that my computer sent to, I don't even know where that is hosted, Amazon, I think. So we're kind of like, hey, we want this data, please give it to me. And then there's a lot of extra meta thing. The interesting thing here, which is the core of HTTP, is you have a path, well, you have a verb of what you can do, as you probably all know. This is a GET request. We have a path, which can also contain all the queries, but that's just the path. And then we kind of say which host do we want to get it from. That is kind of on the HTTP layer. All the stuff about IP addresses that we send it to and all that stuff, that is on the TCP and IP layers. This is just the HTTP, which looks like this. We'll get a response that looks something like this. In this case, the server is actually telling us what you have is already up to date, so I'm not going to send you the content, but the headers of HTTP will look like this. And again, the main part is this first line, which tells us this is HTTP 1.1, and the content you have is up to date. And that is really all I want to say about HTTP, because now we're going to look at some other thing. We're going to go one step back. As I said, like HTTP sits on top of TCP, and TCP sits on top of IP. But as you know, nowadays nobody should be using HTTP. We should all be using HTTPS. And the S stands for secure, and that is what TLS is, which is transport layer security, which can be used in other things than just HTTP. And we should all be using secure communication. So TLS encrypts the data streams in both directions, and it sort of ensures it can ensure to both ends who the other end is. Which is a thing a lot of people forget about. But let's say I'm sending my super secret bank password to my bank. There are two things I want to be sure about. One thing is that it's encrypted so that nobody can read the password while it's on the wire. But I also want to be sure that I'm actually sending it to my bank and not some hacker. And TLS solves both of these problems. It can actually, although that's very rarely used, the server can also get a guarantee about who the sender is. Very few people use that, but you can actually have a certificate. You have a certificate on the server usually. You can also have a certificate on the client so that the bank knows who is contacting me. That is TLS. And when you're using TLS, what really happens is we in this kind of layered approach, we just slip in another layer, so then HTTP will run on top of TLS, which runs on top of TCP, which runs on top of IP. So HTTP doesn't change, and TCP and IP don't change either. The thing about TLS is that on top of everything else that is happening, TLS also requires a three-way handshake, and that is another thing that is very important to remember, which we'll get back to in a bit. The other side note about TLS is that in iOS 9 there's this new thing called App Transport Security, and the security is very complicated. We all read about all these hacks that happen all the time, and it's very, very difficult to get things right. And with iOS 9 and ATS, it's become somewhat easier. TLS can run in all kinds of insecure modes, and unless you mess with your info plist, iOS 9 will refuse to connect to a server unless the TLS connection fulfills a certain level of security. Like all the modes that are known to be very easily hackable that you can usually do with TLS are disabled. That was the theory. I think I have 3 minutes left to tell you what to take away from all of this. So why do we really care about all this IP and TCP? I mean, we can just use NSURL session and we're all happy. Well, if you're putting the pieces together, one important takeaway is that creating a TCP plus TLS connection is very expensive. The TCP connection has to do a three-way handshake, and the TLS connection has to do a three-way handshake. So the data has to go back and forth between the client and the data just to create the connection. At that point, we haven't sent any data to the server or received any data from the server. And if you're on an iPhone and you're not on Wi-Fi, you're somewhere out in Spain on a bus, then the time that it takes for a packet that leaves your iPhone until it reaches the server can easily is a lot of milliseconds, and when you have to ping back and forth on that data, it can easily take half a second, and it's not unusual to take more than 1 second just to create the connection. So let's say you want to download a tiny piece of JSON, maybe 20 bytes from a server. Moving 20 bytes, even on an edge network, is going to take a fraction, or it's just going to take very, very few milliseconds, but you'll have to wait 1 second until you can start sending a request for those bytes or sending those bytes. And that is really important to remember. The other part is that TCP has all this clever logic and is very good at using the maximum bandwidth, figuring out that some data got lost and need to retransmit it and all those things. But it can only do that while the connection is active. Only when packets are being sent back and forth can TCP make some qualified guesses as to what it should do on the network. When you have a connection that has very little data going, TCP doesn't know what the network is like. And particularly when you just created a connection, TCP hasn't really sent any data yet. So it doesn't know if you're on a gigabit Ethernet or if you're on an edge network somewhere in the middle of Spain. So putting those two pieces together, the really important takeaway is that as much as possible, you want to use one connection and reuse it for everything. You want to push all your data that your app uses, that your app needs to communicate to a server through a single connection. Because that way you only pay for the setup cost once, and that single connection is as active as possible. So TCP, all those clever algorithms, can really be put to use. And how do you use only one connection? Well, one thing is you want to, as much as possible, make sure you only talk to one server, which can be difficult. But back in the day, until very recently, when people built their backends, they kind of had lots of servers because they were kind of spread things out. Nowadays, that's actually a very, very poor design. You want to make sure you have one HTTP endpoint. So you're talking to that one server. And then what you really want to do is you want to switch to HTTP2. I mean, HTTP2 is still very new, but most cloud providers out there, Amazon not, because they're super slow, but they're also getting there, support HTTP2. And what HTTP does is exactly that. It uses a single connection, and then inside that connection, it's like you have to imagine a big pipe that is the TCP connection with the HTTP2 connection. Inside that pipe, the single request can be sent back and forth. And it can even do things like figuring out, I have another request that is a high priority, so I'll wait sending back the other ones. And what people are seeing, that particularly for slow requests, for small requests, which is what you do when you do use REST APIs, you often send small amounts of data back. HTTP2 can give you a dramatic boost, and particularly again when you're on slow networks with high latencies. So this is available in iOS 9. It's to some extent available in iOS 8. iOS 8 had the predecessor to HTTP2, which was called Speedy, which is automatically supported. So if your server supports HTTP2 and or Speedy, it'll work automatically as long as you use NSURL session. Yeah, that was that. There's a link where you can actually check if a server supports it. The other nice thing, particularly for small payloads, is that as you saw, HTTP has a lot of headers, and those are actually compressed. So if you're sending your 20 bytes of JSON and you have 400 bytes of headers, those can actually shrink down. It can make a huge difference. A lot of us either have a server that doesn't support HTTP2 or are on some older OS. So there, what is really worth checking out is a pipeline, which is a very old feature, but it's off by default. But this combination is what this RFC 2616 recommends. And it gets you very close to HTTP2 as long as you're only sending GET requests. There are some limits in the HTTP standard. So when you do post or put, the connection actually has to be torn down and a new connection has to be created. So pipelining doesn't buy you anything. But for GET requests, pipelining will allow you to continuously reuse that one connection. And the recommendation is actually, in this case, because it's not as clever as HTTP2, the recommendation is to use 2 connections per host. And almost the last slide is about security. As I mentioned, use app transport security, don't disable it. The other thing that you may want to think about is pinning your certificate. It's slightly difficult, but if you Google it, you'll find some hints on how to do that. There are 2 options you can do. You can either pin your server certificate, which is more secure, but also makes upgrading your servers a bit more complicated. What you should, at the very, very least, do is pin your certificate authority. If you have a server, and I connect to your server, then you have a certificate from some certificate authority. Now, if somebody wants to hack into that connection, they might bribe some certificate authority in some country where it's easy to bribe, and they can get a certificate that my iPhone will then think, well, this is really that server. It's kind of this guarantee that TLS gives, because this certificate authority that was giving this away for some piece of money tricks my iPhone into trusting that connection. If you pin your certificate to that authority, only certificates from the authority where you bought your certificate will be trusted. It's kind of it's a good middle way. And those were the words. Thanks for listening, and if you have any questions. No questions. I hope that's because the talk was good. No, there are questions, yes.
I have 2 small questions. First was about, you talk about this ATS, the app transport security. How does it really affect? Because one of the things you use HTTP only is because it was like less CPU used on the server side, less load. Also, it was faster. How can you just do that now?
Well, you can turn off app transport security, and then you can do HTTP. But the thing if you use HTTP, there are 2 instead of HTTPS. There are 2 things that you lose. One thing is that everybody can read the data on the network, but it's also everybody on the network can pretend to be the server that you're talking to. So of course you don't want to send any passwords and stuff over HTTP. That's kind of obvious. But the thing you also need to think about that it's quite easy for somebody else to pretend to be a backend. So your app that displays some photos, if it gets those over HTTPs, it's very easy for somebody else to get in the middle and send you photos that maybe you don't want your users to see, of naked people and I don't know what. And that's also the thing that HTTPS gives you. It's not only because this is super secret data, but it's also I want to be sure that I'm getting the data from my backend and not somewhere else. And if you just use HTTP, it's trivial for somebody else to get in between you and your server and do other stuff. So you should really not use HTTP for anything, because there are a lot of non-obvious security things, even when the data seems like it's not something that is secret. But HTTP is faster, but again, if you switch to something like pipelining or HTTP2, you only pay for the initial setup.
And with HTTP2, how does it play with inverse proxies or CDNs or load balancers? So
most of the companies that do CDNs and load balancers support HTTP2. I mean, HTTP2 is still relatively new, but more and more getting on board. Amazon being the black sheep, they're a bit slower because their infrastructure is larger, but they're also going to support HTTP2. They're actively working on it. And a lot of the other providers that are smaller already support HTTP2. So unless you're creating your own server that you sit somewhere in your office, it's probably not something you have to do. It'll just work. And yeah.
How would you compare HTTP2 with the WebSockets?
It's a different thing. Sorry? The question was, how do WebSockets compare to HTTP2? And a WebSocket is a way to use HTTP to kind of be able to send data both ways. It kind of turns your HTTP connection into something that looks like a TCP connection, which is kind of weird. You can run a WebSocket inside HTTP2 as long as your server supports it and the client supports it. So it doesn't really have anything to do with that. It's I'm not sure what the support is on the server side, because obviously they have to terminate that in some way, but the protocol allows it. And NSURL session, as far as I've seen, supports it too. Particularly the new IS9 has some nice APIs for that.
Actually, there is a protocol extension. It's called multipath TCP, and it allows switching from Wi-Fi to cellular network, or use both methods on the same time. And it's implemented in the iOS 7 version, and you can use it.
Yeah, it's not really.
Actually, it's used by the system in the background without you knowing that. Multipath TCP.
I don't think it's I think it's private API though, but I'm not sure.
Yeah.
Anyway, a lot of people have done stuff like that. So the thing is, on the the TCP layer doesn't have the addresses. The addresses are on the IP layer. So you can kind of trick TCP just to send packets to multiple hosts and stuff, and people have done a lot of extensions on that, and iOS actually supports it. As far as I understand, it was mostly done for Siri, so if you're going to talk to Siri, it kind of sends it to both Wi-Fi and the other one, because a lot of times people couldn't get Siri to work when they're on a Wi-Fi. That wasn't working, because then Siri was trying to send for the Wi-Fi and didn't work. So now they kind of send it both ways and kind of figure out which one is working. So a lot of weird edge cases there, but I'm pretty sure it's private API. I actually talked to some Apple people about that at some point, and they're like, yeah, it's in the system, but you can't use it. But maybe I'm wrong.
Oh, okay, it's possible. This protocol, it's open, and it's from 3 years or something like that. It's public.
Yeah.
And it's implemented also on Amazon servers for data centers and other stuff like.
Yep.
Do you have any data that I can provide to the server guys to tell them, yeah, can you just switch so everyone will win?
If you're using Nginx, and Nginx supports the SPDY and the HTTP2. I don't know if it's already in their release branch or whatever it's called, but they're working on it or have it working. I think Nginx has it working. I'm actually pretty sure, and it's just a question of it being deployed. But the server that you run in your load balancer or HTTP endpoint, that software will probably have support for it once you upgrade to the latest version. Sometimes it's something you have to turn on, but most people that have that, unless you've written your own HTTP endpoint, will have support for it in the latest versions. Everybody is switching to HTTP because the gains that you get are just very large. The thing as an app developer is like there's really not a lot you have to do. The thing to think about is that you really want to be sure that all the requests that you make are to the same host. Because HTTP2 doesn't help you if you have 10 different servers that you're making requests to, because then you need to have a connection for each one of them. That's kind of the thing too. You have that one connection, you keep it alive. I mean, the NSURL session will do that for you, but you just have to think, okay, your NSURL session keeps the connection, so you kind of want to use the URL session for everything. it's mostly kind of magic happening somewhere else.
Hi, Daniel. Thanks for your brilliant talk. At the beginning, you told us that in the protocol, in the ACK part, in the protocol, it adds one value to the handshake, and you say that you don't know why. It's for a good reason. Just trying to clarify that the TCP/IP protocol is based on serial communications, and their way trying to avoid a problem that in some cases the wires transmission and reception gets short circuit. So then adding a number, a digit, will avoid the one infinite loop problem. That's why.
Makes sense, yeah. And I actually wrote an article about this that goes into some more detail. This was kind of the super short version, yeah. Okay, cool, thanks. I think that's it. Thank you.